Next slide for me, Russell. So the presentation today will be pretty quick. We structured the program for to try to reach as broad of an audience as possible. The purpose of that is just to have people who are potentially interested in commercializing one of these technologies to reach out to us and kind of tell us a little bit more about themselves. Depending on how much interest we get, we might change some of the application stuff at the end, but we'll just kind of keep the presentation as it is, and then we can talk afterwards as well. The next slide. So the National Laboratory System was founded in 1910. Russell's going to talk about Lawrence Berkley a little bit more detail in a second here, but Lawrence Berkley is actually the second national laboratory. And the National Laboratory System is actually pretty large today. So there's 17 national laboratories. I actually put 3 of kind of the most interesting technologies, outcomes that came out of the National Laboratory System. The quantum dot technology is like the baseline technology in a lot of TVs and e-readers today. So it's one of the biggest commercial successes, I would say, out of Lawrence Berkeley. My background was working for the government for a while before coming back to school to do a PhD at the MS&E program. So I'm really interested in the effect of government policies on firm performance. Part of that research looks at all the spending that goes into the National Laboratory System and its effect on generating returns, private returns for firms who commercialize the technology, and social returns, right? So, you know, the technology gets out there to a wider audience through commercial channels that generates larger social returns as well for the taxpayer's investment. And that was kind of the genesis of the conversations that began between us and Lawrence Berkeley. And that's why we're really interested in seeing if Stanford students want to take a crack at commercializing these technologies. And with that, I'll turn it over to Russell.
Sure. So I'll give you a little bit more background about the National Lab System and tell you a little bit about Berkeley Lab and then go into the technologies. So kind of an interesting origin story of the National Lab. It was founded in 1910, but it really got going after World War II and the Manhattan Project. So for the Manhattan Project, they basically brought in a lot of brilliant scientists from universities flung, throughout the U.S. and the world, and they concentrated them in one place to essentially do big science. Is this idea a scientific project or projects that are too big for a professor at a university, right? So you get hundreds and spend tens of millions, hundreds of millions of dollars on these big science projects. You get things such as the nuclear bomb or nuclear power. You get things such as the Large Hadron Collider, which is the giant track in Europe where they're smashing atoms together to find the fundamental particles underlying the universe. And there are about 15 to 17 national labs, and a total of $10 to $15 billion of funding goes into them. And I am at Berkeley Lab. I was a PhD student at UC Berkeley, but my PhD advisor was a scientist at the National Lab, at Berkeley National Lab, and that's pretty common. Berkeley Lab is government-owned, contractor-operated, meaning that it's funded by the Department of Energy, but it is operated by the University of California. So as an employee of Berkeley Lab, I am actually an employee of the University of California. Just like, for those of you here who know SLAC, the Stanford Linear Accelerator is another GoCo, so it's government-owned and it's operated by Stanford, the contractor. So Berkeley Lab was founded in '31. It's funded by DOE, operated by UC. Very, very impressive scientific resume. So lab scientists have won 12 Nobel Prizes. Couple of different ones: transuranic elements by Edwin Macmillan, photosynthesis by Calvin, discovered photosynthesis in plants. Saul Perlmutter won in 2011, I believe, for the accelerating universe, basically proving that the expansion of the universe is accelerating. And then you can see in the periodic table of elements, everything that's boxed here was either discovered or synthesized at Berkeley Lab. So a lot of good stuff. So the technologies we're going through have this kind of heritage behind them. And to Jason's point, one of our big goals is to transfer our technology to the private sector such that it can benefit society. A lot of research happens and it gets into the public record, like as journal articles, but really that's by scientists for scientists. And we'd like to do better. We'd like to get the technology out there. A couple of different initiatives, I-Core. I'm not sure if you all are familiar with the idea of I-Core, but there's a program specific to national labs to help train national lab scientists and evaluate national lab technologies. But even with that effort, we still have a long way to go to actually get our technology out there. So I have 5 technologies that I have handpicked. I cover about half of Berkeley Lab. I do a lot of the physical sciences, earth and environmental sciences, and material and energy sciences. The stuff that I don't cover are kind of batteries and windows and more, I guess, closer to market technologies, and also biotechnology. So I have 5 technologies that I've picked from my areas, but there's a lot of other technologies that are available. And so if you, we'll have a website at the end of the presentation. If you are interested, I encourage you to go to that website, poke around, see what you find, see what you like. And if you find something that you think is compelling, let me know. These 5, I've already gone to the scientists and got their confirmation that they will be available throughout the quarter to be basically a scientific or technical resource. But just as an example, in the biosphere, the microbiome is a very hot subject, both for human health and also for agriculture. You know, figuring out ways to use the microbiome or curate the microbiome to make crops more productive, for example. And then in kind of the built environment, windows and batteries and energy efficiency, HVAC, all that kind of stuff is available too. So Jason and I and my office have been talking about this, and you know, for a technology that you choose, kind of three things behind you. One is, as I said, you'll have access to Berkeley Lab scientists who are actually the PIs, the principal investigators behind these inventions. Mentorship through Stanford, and certainly from my office to the extent that we can offer it. And then also a first mover advantage. We are, for the technology selected, we are setting those aside. They are currently available for licensing. We will set those aside for a limited period of time so you can do your analysis, and so you know that when you've done your analysis and you come back, we won't say, oh yeah, sorry, we licensed those technologies a month ago, right? So without further ado, we can go through the technologies right for transfer. So for each of these, I'll tell you a little bit about the science, just so to give you some context, a little bit about the application, and a little bit about the competitive advantage of these technologies. So I'm curious if any of you are familiar with chelation in a clinical context. So yeah, it's based in coordination chemistry. So the idea is you have this fat atom, this heavy metal, for example. The heavy metal has a lot of binding sites, and that's what make it. A couple of factors. One is it has a lot of these binding sites, so it gets really tightly bound to organic tissue, for example. And it's also mistaken for a lot of critical nutrients such as calcium. So a lot of heavy metals, your body will think, oh, that's calcium, I'm going to store it in my bones. And then it gets in your bones and it's really, really bad. So what's been developed is essentially a very, very powerful chelator. A couple of different applications. It can be used to treat and prevent gadolinium deposition in patients undergoing MRIs. There's also a lot of quote-unquote radiomedicine happening right now. So the idea of using radioactive materials to both treat and diagnose disease. And so this is a potential tool for helping to manage and improve those kinds of interventions. Some of the advantages, this molecule that's been developed has very high selectivity, so it's very good at going and targeting the heavy metal without leaching calcium or magnesium or zinc from your body, which is a huge concern when you're talking about chelation therapy, because most chelators are indiscriminate. They go in, they grab every kind of metal, and they allow you to excrete it. For this molecule, it uses the liver excretion pathway. Basically, 2 ways out of your body. You poop something out or you pee something out, right? And a lot of these chelators use the kidney pathway, so you essentially pee them out, but if that's the only route taken, things tend to accumulate in your kidneys, and that can be toxic. So those are a couple of advantages for this technology. Any questions on this one? All right, okay. And as we go through, if you guys have questions, interrupt me or ask them at the end, either way. Yeah?
One question, how did you guys get to this from?
Great question. Yeah, great question. So the scientist behind this is a nuclear chemist, and she was approached by actually the Department of Defense to develop a chelator for dirty bomb countermeasures. So if there's a dirty bomb, it's not necessarily the shock wave or the fireball that you're worried about, it's the radioactive fallout. And radioactive fallout, remember so basically these series right here at the bottom get plugged in right there, right? These are the lanthanides and the actinides, basically the transuranics. All of these are considered, the transuranics. They're extremely toxic to life. And those are the byproducts of these dirty bombs. And so the scientist was funded by the DoD to essentially develop a drug that in pill form can be taken to help the body excrete nuclear fallout from a dirty bomb. And so fortunately there's not a lot of market for that. Started thinking about what else could this be used for. And there are applications in human health. As I mentioned, radiomedicine is becoming more and more popular. There are also applications in nuclear waste management and remediation, splitting out the good, byproducts of nuclear fission such that they could be reused again, that kind of thing. The next one is a LiDAR periscope. So are you guys all familiar with LiDAR, using it to map out the physical world around an autonomous vehicle, for example? So the basic idea, the name says it all, it is essentially a periscope that allows you to use a LiDAR not in a line of sight of what you're trying to image. And this has a number of different applications. You can imagine, an autonomous vehicle, at the simplest, an autonomous vehicle driving down the road with this giant bulbous LiDAR thing spinning around, right? That's really bad for efficiency. That's really bad for physical performance of that device. You can imagine trying to build a drone that has this giant LiDAR appendage, so it's bad from a performance standpoint. And then also, hiding the LiDAR allows you to put form factors and fairings and things like that around it such that you can improve the aerodynamics, you can improve the aesthetics. It also ruggedizes LiDAR equipment. If you're in a military context, right, and you're trying to map out the environment around you, if you stick your LiDAR thing out into the open such that it can see what it's trying to image, first thing an enemy's going to do is just shoot your LiDAR, right? It has to have line of sight. So the idea is you could have your LiDAR in some kind of protected environment, send, a bunch of mirrors, just like a little periscope around the corner. They shoot that, no problem, put a new one on. Those cost pennies, whereas LiDARs cost hundreds of dollars and are very finicky. So that's the idea here, is that you can use this technology to essentially improve the aerodynamics, improve the performance, improve the aesthetics, improve the ruggedization, for lack of a better term, of LiDAR-equipped devices. And it's one of those, I really like this one, because at a national lab you get a lot of very early stage technologies that are, they can be used for everything and nothing at the same time in the future, right? You don't know. But this one has, it's one of those technologies that has a very clear kind of here's the application. You want to make a better self-driving car, right? You can use this to improve the aesthetics, improve the performance, etc. Any questions on this one?
I have a question on this one. So is the technology about the, how you create the periscope? Is it the materials that you use, or is it the
LiDAR itself?
Refract the.
Yeah, so it's it's definitely not the LiDAR.
Yeah.
It doesn't care what LiDAR you use. It's essentially the idea of mirroring passageways, and then it's almost a question of geometry, right? Because you're sending your LiDAR out, you're bouncing it around some number of times at some angle, and then out it goes. It strikes something in the physical world, it gets reflected back, it bounces all the way back. It's the core of this is both the idea of putting it in kind of like a mirrored hallway, if you will, and then the algorithm that is used to account for that mirroring and figuring out the path that this, the laser beam essentially took through this, such that, if you have something bouncing 50 times, that might add 50 feet to the path that laser beam has traveled. So if you don't correct for that, when it comes back, you think that thing is 50 feet farther away than it is, right? So two pieces of IP. One is just this idea, and then the other is the algorithm that allows you to back out the signal that you're getting back to the built environment around it.
Is LiDAR currently being used on EVs, or autonomous vehicles?
So LiDAR, yes. The periscope, no. The periscope was developed as part of a Department of Defense program. Actually, they're obviously very interested in both ruggedizing equipment, but also doing security. And they want to, if you're at a football stadium, right? They want to be able to map out the physical environment of that football stadium without sending everyone into a panic, or making everyone like, what's that guy doing? What's that guy doing? He's got a LiDAR thing spinning on his backpack, right? You don't want that. You want something that's discrete, that allows you to take measurements and kind of a low key is not the right term, but maybe it is, right? And you want to be able to take low key measurements. Okay, so here it's essentially a system for characterizing the quality of fractures, and fractures, geophysical fractures. So the idea is in fracking, you pump down a whole bunch of high pressurized fluid with some grains and whatnot, and what you're trying to do is you're trying to shatter rock, right? But the problem when you do this is if you've shattered something, but you can't characterize that shatter. You don't know if it's been in plane, because generally oil and gas, also geothermal resources are generally in a horizontal layer, right? If you think about like the layering of the soil, the asset that you're looking for, whether it be oil and gas, whether it be geothermal, is generally in a horizontal plane. And so if you fracture, it is much better if you fracture in that plane than if you fracture vertically out of the plane, or if you simply slip, right? You have these planes, and if you shear along those planes, that's very, very less valuable than if you do a nice fracture in plane. And what people do right now is they essentially fracture, and then they say, well, what did we think we did, right? And then based on their guesswork, they say, do we want to invest millions of dollars in trying to build out a rig for this geothermal well, or this oil well, or this gas well? And so what this technology does is it essentially allows you to understand what kind of fracture happened, so you can more intelligently invest your money in this well, or that well, or this other well. And the way it does that is essentially you can drill some holes. You don't have to go all the way down to the fracture site, but you drill some holes, you put some sensors in here, and you essentially listen. It's almost like acoustics, like seismic sensing, right? You listen to the acoustic waves that propagate from that fracture, and based on the signal that you get and the arrangement of your sensors, these scientists have created an algorithm that allows you to back from what the sensors have perceived to what kind of fracture happened. And And as I mentioned, it's essentially a way to more intelligently invest your resources in this well versus that well versus this other well. And again, it can be for oil and gas recovery. It can be for geothermal. It's possible that it could be for example, water. You know, if you have an aquifer, or if you have water bound, could potentially be used for that. Essentially, any application, and this is actually part of what we would love to learn from you if someone decides to commercialize this or evaluate this, is what else could it be used for? You know, there's a lot of potential applications. Any questions on this one? Yeah, please.
What sort of testing has been done? I've sort of walked in it, so I don't know
Yeah.
what the stage is, but what sort of testing has been done on this one?
Yeah, so all of these technologies have been published in peer-reviewed journals. So I think this one was Nature. I think most of these have been developed and published on. It's pretty rare that we have a functioning prototype that has been. If you guys are familiar with TRL levels, the technology readiness level, it's pretty common in DOE and DoD technology development. Basically, one is I've had the idea. Two is I've written some back of the envelope calculations down. Three is I've synthesized something in the lab and it didn't blow up in my face. All the way to 9 is it's in the market. 8 is it's been tested for 4 years or 5 years by a relevant company doing the thing it's supposed to do, that kind of thing. So it's this gradation. Most of these technologies are somewhere between, I would say, 3 and 5, where they've the scientific principle has been demonstrated and published on, to maybe moderate scale up, or whatever the equivalent is in that technical field. So I know this one has been tested in the field. It's been published several times, presented on several times. I don't know, for example, if an oil and gas company has tested it. Our scientists are always collaborating and looking for a path forward, a technical development path. But I admit I don't know the details for each of these. But yeah, they're at a minimum, they've all been published on in peer-reviewed journals. This technology is essentially recyclable plastics. And so a little chemistry lesson: when you're developing these plastics, you start from a monomer, right? That's your single molecule, and then you polymerize those molecules through something called a condensation reaction, where you're generally using water to react the monomers and make them stick together, right? But that's not the final plastic product. Final plastic products have colorants in them, molecules to color the plastic. They have flame retardants that are used to prevent, your plastic chair from lighting on fire as soon as it gets close to a source of heat. You have a lot of these kind of adulterants, colorants, flame retardants, plasticizers, whatever property you're looking for. And that's part of the reason when you recycle plastic, it's almost entropic in the sense that it always goes down in quality until it cannot be recycled anymore. And that's part of the reason is in your plastic products, you have all of these adulterants and there's no easy way to get rid of them. So for example, let's say I have some blue plastic and I have some green plastic and I want to recycle that. There's just taking salt and pepper that are separated and shaking them, you get some homogeneous gray color. You'll never shake it and have that, green and blue separate out again, or that salt and pepper separate out again. That's kind of what happens when you recycle plastics. You put all of this plastic in there, you blend it up, and at some point you get a weird grayish brown color that cannot be reversed. And so that's kind of the last stage of plastic recycling, and then you're done. So what these scientists have developed is essentially a life cycle chemical process that starts with the monomer, allows you to polymerize. You can add all the colorants you want, all of the flame retardants you want, all of these adulterants, generally speaking, you want. You can use the plastic. It has equivalent performance, toughness, plasticity, conductivity, all of kind of the general properties that you're looking for in a plastic. at the end of it, a very, very simple chemical process will essentially dissolve that plastic, separate out the flame retardants, the colorants, and you're left with pure monomer. Again, it's depolymerized fully. And it's generally called dynamic covalent bonds is kind of like the foundational element to this. It's the idea of chemical bonds, covalent chemical bonds that are pretty reversible, that are strong in the moment, but generally chemically reversible. So here they've done tests where you make something, you add a bunch of color and a bunch of flame retardant to it, you blend it up, and then you reverse that, and you get out this white, pure monomer. They've done it with, plastic garbage that they've purchased from, a recycling plant. They mix it all together, they put it into acidic solution, dissolve everything, whereas before, maybe you could turn that into some kind of dull gray, cheap plastic. They are able to reverse that and get out their monomer and completely separate out their monomer. Applications, essentially anywhere where recyclability is becoming important. Europe in particular, Europe is way ahead of the US in terms of producers having to understand and account for their plastic, their technology throughout its life cycle, all the way to disposal. It's becoming more of an issue in the US now that China and other companies are no longer accepting US plastic for the most part. It was, we were basically sending everything to China and they were just dealing with it, and honestly most of it was just dumped. But now they're saying we don't want it anymore, we've got other things we want to do. So this idea of recyclable kind of cradle to grave engineering of a product is becoming more and more common. One example that's kind of interesting is there's a business question of, well, what does recyclability give me unless I own it at the end and I can take advantage of this, right? Because you have this problem of payer and benefiter being separate. If I sell to company A and they pay a premium, but they're not actually able to recover on the back end by, capturing the value of this recyclability, it becomes difficult. So there are ideas around, companies that own an asset throughout its life cycle and are becoming a service company, whereas maybe before they were simply a product company. So you can imagine let's say a car company is starting to lease their cars or has fleets of cars that they own and they lease out as a service. The interior of the interior of the car is people are very sensitive to that. Scratches on the interior of a car, maybe the actual mechanical structure of the car is perfectly fine, but the interior is degrading, right? That's going to diminish your ability to license it to the next person, or lease it to the next person, because they are going to perceive that finish to be of poor quality. You could potentially basically strip out all of the plastic interior, break it down, remold it, put it back in perfectly fresh, without having to do this degradation of quality. That's kind of an idea of this, life cycle. The company that creates or sells the product is ultimately there to benefit on the back end from the recyclability. Any questions on this one? A couple of things that I didn't mention is, low volatile organic compounds. Those are becoming a huge concern when you think about indoor air quality. Every plastic you see gives off a bunch of volatile organics, and there are increasing number of regulations around how much a product can actually give off. We didn't get one. There it is. And this one is like very DOE. It's essentially an ion accelerator. And kind of like most of our technologies, it has a pretty out there original application, why it was funded, basically for fusion. To do fusion, you have to, energize these particles up to speed them up to near the speed of light and get them reacting and hopefully fusing. But there are actually a lot of applications of ion accelerators, more than you would think. Material processing, for example, semiconductor manufacturing. When you're making your p-n junction, right? How do you get the boron in there? How do you get the phosphorus in there? You basically take a silicon wafer, take an ion accelerator, and shoot it with these ions. And when you think about one of those, it's about half of the size of this room. And to accelerate the ions, you need millions of volts. which is extremely dangerous, extremely expensive. This technology, you're going from essentially a structure half the size of this room costing $8 to $10 million to something about that big. And it doesn't have these million volt standoffs where you need, people with 5 degrees to operate it, right? It uses something called radio frequency acceleration, which is pretty brilliant. Basically, as the ions travel through this, you're swapping out pluses and minuses. Because as soon as you pass through one of these gates, let's say you have a positively charged ion, you want the side that's repelling, you want that to be positive, the side that's going toward, you want that to be negative, right? So the positive thing moves towards the negative and is repelled by the positive, right? So it's accelerating that way. As soon as that passes that, you got to switch it, right? You got to make that the new positive and the next one the new negative, such that it will keep accelerating away. If you don't switch, then it flies through and it's like, oh, there's no negative charge back here. I want to decelerate and go back to that. So you basically do this staged gating where you're swapping these voltages, and it allows you, as I said, to avoid these million volt machines where they're gigantic. They require a ton of power. They require a ton of expertise to operate. And as I mentioned, there's a lot of. It seems like kind of a wonky technology, but there are a ton of commercial applications. So I mentioned semiconductor manufacturing, exfoliation of materials, homeland security screening. Essentially, if you wanted to understand what is in my bag, right, you can hit it with some of these charged ions. It will interact with the material in there and it'll kick out a signature that you can detect and say, this guy's got uranium in there, or he's got something else. And there's a lot of use in pharmaceuticals, medical, environmental science for these ion accelerators. So that's that one. Any questions? No? Okay.
So just in terms of the readiness, this is probably high, right? Because you've already got a product.
That is a scale model. It has been built. It has been built out to here. So this is 4 feet long. Obviously not to scale here, but we have about 2 feet of it, and it's linear in the sense that that was part of the idea, is to basically decrease the size of these things. And each of these wafers here is a MEMS based wafer, so it's just silicon with some circuitry on it. But yeah, it's one of those, once you prove this part, that's the principle has been proven in adding different links to go to higher and higher energies. It's not trivial, but it's not nearly as difficult as getting the principle working in the first place. So yeah, this one, I would say this one is around a 4 or a 5. Are you guys familiar with ARPA-E? It's ARPA-E is essentially the DARPA of the Department of Energy. So the DARPA for the Department of Defense was like their skunk works, super far out there technologies that might completely change the way something is done in the future. The Department of Energy saw that, was like, that's a really great idea. We want to form our own DARPA equivalent, so they called it ARPA-E. But this has been funded by that. There's a funding opportunity right now that could be another few $1 million to develop this. So that it's in development now. Any other questions?
How much is that? That thing?
If you were to buy it, original ones, you're talking $10 million, something like this. Something like this would cost $1 million, maybe $1.5 million, and it would be a substitute. The other advantage is when you have these. The standard is you basically have one stream of ions going in, so you raster across the surface of whatever thing you're trying to deposit these implants, or you're trying to implant these ions in. This actually has 9, so it's a 3x3 grid. So imagine it's like you're spray painting something, and your spray can produces that big of an image versus that big of an image. You can do things much faster, much more efficiently. And there's also one other advantage is generally you don't have precise control of the energy of these ions as they come out of your system. And if you're if you're trying to make a p-n junction, right, the energy of those ions is going to determine how far into your wafer that ion is going to implant. So you really want to concentrate them in like a narrow band, or a narrow horizontal plane in your wafer. So you need to do some kind of screening, such that if ions are too energetic versus not energetic enough, you want to be able to filter those out. That's something that these giant systems need. You generally use a magnet to do that. You have this like magnetic field, and as the ions pass through, only the ions are going to be bent because of this magnet, and only the ones that are the energy you need are going to be bent in just that angle. So you collect them at the angle you want. This has that functionality built into it. So you're able to avoid this like tabletop sized magnet that can be expensive and finicky and all that. So it's got a lot of advantages. It's one of the more disruptive, although it isn't, as I mentioned, it's kind of a wonky science relative to something like a LiDAR with a bunch of mirrored walls coming out of it. But it's very cool. A couple of success stories. CO is a lithium-ion battery company. They raised a whole bunch of money, acquired by Bosch. These are obviously some success stories. Second Genome, I mentioned the microbiome, bacteria in your gut, on your skin, in the soil, basically in the environment around you, has a profound effect on both you and the environment. This company essentially made a tool for understanding the microbiome and trying to develop products based on that, be they pharmaceuticals, be they soil amendments to try to improve, the microbiome around roots and crops, etc. They've raised a bunch of money too. And Nuomics does these personalized healthcare platforms. I don't know the details of their technology, but they raised about $4 million last month. Any questions on this? Cool.
Awesome. Thank you, Russell, for that. I try to make this pretty quick. So, just to tack on to what Russell said about the technologies. These technologies are available for licensing today. So the kind of key part of what DOE agreed to do and Lawrence Berkley agreed to do coming down here was to say that these technologies that Russell has highlighted are ones where the scientists are interested in working with you in developing a business model around the technology, and willing to set aside these technologies so they're not available to license outside of what you guys are working on until the end of the quarter, essentially, right? So there's basically kind of guaranteeing you that they're going to set the technologies aside while you work on them. All other technologies, and this is kind of a broader statement, and I'll show this in a second, but all of the technologies that the DOE has available to license are kind of available online. So if there's something here that you're interested in doing this, you kind of like this tech-focused aspect, but maybe one of these technologies isn't really your shtick. Maybe you're really looking for energy storage type of technologies. As Russell mentioned earlier, and as some of you came in a little bit later, but there's folks that Russell can absolutely help to try to build the connections between, and maybe even add it to this list. So highly encourage you guys to do that. As far as these specific technologies, what we'd like you to do is, if you're interested in working on one of these 5, if you could just send us no more than a page of like an application, but really just tell us about yourselves. If you're taking a class this quarter, what that class is. It's not necessary that you have to be taking a class, but this program is really designed to be paired with a class, because what we're hoping to get out of this is both information for yourselves to see if this is a viable technology to build a business around, and that information for the laboratory, so that the laboratory understands what you guys have to say about potential product market fit in the future. Because right now the taxpayer is funding the bill to license these technologies, right, and to do all of the patent litigation and stuff that goes along with developing a defensible technology. So it's important for the laboratory to learn about that. It's important for you guys, if you're interested in building a company around it, to learn about it. And so if you're doing a class, it's really easy, because whatever the product is for the end of the class is something that we can take and build off of. If you're not doing a class, then we just need to work on, what do you think you can provide by the end of the quarter anyway. So these are the things in the application process. Really just tell us about yourselves, what you're interested in. If you're interested in more than one, that's okay too. And then after that, we'll do some quick evaluation, and if it looks like it's going to be a good fit, then Russell will introduce you to the PIs who are in charge of the technology, and you guys can have another conversation. You can have that conversation about TRL levels or about how close it is to being a product, and you can kind of dig into the technology a little bit more detail. Please send the applications as soon as possible, just so that we can build those connections. Especially if you're taking a class, you guys are already a week into classes, and there's only like 9 weeks left, right? So we want to be there and make sure that we make these connections as quickly as possible. So by Wednesday, if possible, send those applications. Yeah, so if it doesn't look like it's going to be a good fit, or maybe you talk to the scientists and you're like, well, we can't just come to an agreement on how we'd like to work together on this. Like I said, please check out these websites.
Yeah,
that's the Berkeley site.
This is the Berkeley one that I mentioned. It's got all of our microbiome and agriculture and batteries and windows and all that kind of stuff. And then, as Jason mentioned up front, the National Lab Network is 15 times bigger than Berkeley Lab with 15 times more funding. And so every national lab has someone like me that manages their portfolio, and they're all kind of aggregated here, or at least links to IPO.LBL, IPO.Argonne National Lab, .Livermore National Lab. All those kinds of things should be linked from here.
Just before we wrap up, some things I heard you guys mention that I think are important things to take away from this. First, the technology development lifecycle. Since these technologies are in the laboratory system, they're already receiving government funding, right? There's more government funding normally available, even after the stages that they're in. So a lot of these technologies, because they're coming from these DOE programs, they have additional funding possibilities that are non-dilutive, and there's all these kind of public funding things that come attached with that, but there's potential for additional funding that may not be the traditional kind of capital raise that you guys might be looking at when you're on business classes or whatever. So that's something to keep in mind. Yes, and then the other thing is, when you talk to the scientists, if you guys end up making these connections, ask them about the existing markets they're kind of currently thinking about, right? Because they already have an idea of where they think this technology can go, and I think they can provide a lot of additional information. So with that, thank you guys for coming out today. Just maybe wrap up. Do you guys have any other questions or?
In terms of, will you guys do this every single quarter? So if next quarter I'm going to take a course which is going to be entrepreneurship, do I just go on the website, or do you guys do this every quarter?
Well, welcome to the inaugural time. So, to be honest, I think we'll see how this quarter goes. Whether we do this or not, the technologies are always available. I think what we're trying to do here is really build those connections between you guys and the scientists that are building these technologies, right? Because personally, I think that's kind of the main link that's missing. We'll go, as we go through the quarter, we'll kind of make the game time decision of when to do this. But in the application, if you're interested in one of these and you're saying, hey, I can't take it until next quarter, then it's something that Russell and I can talk about and say like, hey, maybe we'll try to push this technology into next quarter so you can go and build on it then. And then maybe you have some runway lead up and you can start the conversations now for the potential to do that. I understand this classes happen all year long, so.
I'm sorry, I'm just a bit confused as to what you mean by you have to take an entrepreneurship class. Do you mean like you need to have a class where you can incorporate this into like a project for the end of the quarter? Or, I guess I'm just a bit confused by that.
Sure, yeah, so I think the key thing for us is just having a product at the end of the quarter that says, this is what I'd like to do with this technology. This is where I think, the market, that would be the first market. These are other verticals we can go into. We're right? If you're taking a class where it's a project, it's easy because you guys are doing that already, right? If you're not, that's also okay. We just need to talk about what that's going to look like.
Sure.
What were some of the original problems you were trying to solve by putting this together? Is it that scientists don't have the time or expertise to launch this on their own or have access to the right people? Is it like not enough funding to hire people full-time to do this?
Yeah, that's a good question.
Yeah, I mean, a little of all of that. Scientists need help. You know, they're scientists. As I mentioned up front, we do have entrepreneurial programs for scientists where it's pretty miraculous, like the change that can take place even like over a 6-week program where it's a classic scientist presentation where every slide has 7 charts on it and you don't know what's happening. And toward the end, you know, there's a very clear story. So we do have training for scientists, but it's not nearly enough. And there's actually an increased focus on entrepreneurship and interest in entrepreneurship on the part of scientists, but you know, they are very rarely going to be the CEO of their own startup, right? They would probably have a CTO type role or maybe a seat on the scientific advisory board where they're able to keep their position at the lab or at UC Berkeley. It keeps them at the front of their field. They can introduce a lot more doors than maybe they would if they were, you know, because they're a professor at Berkeley or a senior scientist at Berkeley. So there's that need, and then like I'm only one person managing about 500 technologies, so I can only, you know, due diligence on so many of them, and I think these are some of the better ones as I mentioned. But yeah, it's looking for help and education on some of these technologies. You know, as Jason mentioned, that's part of the quid pro quo, right? If we make a scientist available to you for 2 to 3 to 5 hours a week, and we put these technologies to the side and don't let other people license them for a couple of months, what we would like is to understand what you think is the opportunity. And it could be, you know, you evaluate it and you decide, you know, there's nothing here, or maybe there is something here, it's just not what I'm looking for. We would like to know that.
I think, yeah, and then just to add on to that, you know, a lot of it's just to make you guys aware of this technology ecosystem that exists and is available to entrepreneurs. I mean, you know, the I-Core program is that training program that Russ was talking about. There's a lot of money going into this training scientists to think like entrepreneurs, but you know, the rarity that comes with the scientist actually leaving a scientific role, I think begs the question of, you know, what are the additional steps that from a national sense or from a policy sense can we do to connect these scientists to commercial opportunities?